afternoon, everyone. My name is Rishan. I'm an investor over at CoinFund. CoinFund is among one of the first crypto-native VC firms. We've been investing since 2015, and kind of in our 9 years of investing, we've backed over 100 teams that are working broadly across the space in Web3 and decentralized technologies. One of the specific areas that we've been spending a lot of time looking into is how different teams are applying blockchain primitives in the development and also distribution of artificial intelligence. And I have the absolute pleasure today to get to chat with Ben Belding from Jensen AI. So Jensen is working on a decentralized compute protocol, also one of our portfolio companies. Ben, it's nice catching up today. I guess maybe frame the conversation. When it comes to the problem that you identified when you first started working on Jensen, how did you see that emerge, and why the particular solution that you decided to approach with the protocol?
Sure, yeah. So I guess I'll kind of briefly explain what Jensen is, and then I guess, yeah, where the problem came from. So like Rishan mentioned, Jensen is a machine learning compute protocol. Essentially, we connect up all of the machine learning capable compute hardware in the world. So GPUs, TPUs, CPUs, anything that's capable of training a neural network, essentially, is connected up on one side, and then on the other side, you have machine learning engineers and researchers who right now, when they want to train a model, have to go to Amazon or Google or Azure or rent or have their own hardware in a data center. Jensen offers an on-demand way to access essentially any GPU or any TPU in the world at a fair market price. And the problem itself, I think now is very clear. It's access to compute hardware, and we kind of see with the rise of ChatGPT, with all the chip shortages, it's a pretty well-known problem. Like, everyone's relatively aware that that hardware is limited and it's only going to the larger organizations. People are raising enormous investment rounds because 70-80% of that investment is going to go towards hardware. But when we originally started Jensen, that was a little bit less known. So 3.5 years ago, we started Jensen with the kind of view that this would happen. And my background specifically is in machine learning research. So I did my PhD in deep learning, focused on neural architecture search. And essentially, I was sat in a PhD lab with 4 GPUs under my desk at my feet, and I was reading papers from Google where they were using thousands of them for weeks at a time to train the same models and do the same techniques. What I realized was I had all of the other things that I needed to do those techniques. I had access to the data. It was all open data sets. I had access to the kind of knowledge of how to build these models because lots of stuff was being published. It was on archive. But the one thing I didn't have access to was compute. And then when you look at the compute market itself, there isn't necessarily a really good reason for that other than distribution. The large organizations that have most of the GPUs are able to charge enormous profit margins for access to those GPUs because they're the only people that can handle the distribution. And so we looked at this as Jensen, and we kind of said, well, how can you smooth that out? And we'd been working on distributed machine learning technology for other use cases. So we were doing federated learning for privacy reasons, modeling of data that for jurisdictional reasons can't be moved. And we thought, okay, well, if we could model over all these different data silos, can we model over compute? And can we essentially solve that kind of access to compute problem? And when you go down that rabbit hole, you get to a kind of essentially a trust or verification point. You think, how can I make this sort of network the largest it could possibly be? How can I make it so that somebody can train a machine learning model on literally any device in the world without having to know the person that owns the device? And there's lots of kind of services that have spun up to solve this, and typically those services are centralized, and they do KYC on the owners of the devices. They put contracts in place, they have SLAs. If you breach them, you can be penalized legally. We wanted to do this purely programmatically, so remove all of those administrative overheads, all of those costs from that problem. And the kind of way you do that is via verifying machine learning compute done on a completely untrusted device, so that the person who submitted the task and sent the task to that device is happy that the task has been done correctly. And ultimately, when you go down the rabbit hole of verifiable computation, you come to a limit where to break a dispute between two parties over a computation, you have to have a trusted third party. And the sort of light bulb moment, and to bring it back to what we do now, the light bulb moment for us was realizing that a chain can be that kind of arbiter. It can be at the consensus of everyone, that trusted third party essentially, without having to trust someone else. And that was a pretty incredible moment for us. And then after that, it was trying to figure out how you can make something like that at all efficient. Because you obviously can't run a machine learning computation fully on the chain. So the sort of secret sauce of Jensen is taking a big off-chain machine learning training task and distilling it into something that a blockchain can verify all the way back up to the full computation. So there's lots of kind of techniques to whittle down that computation into a small proof that can be put on the chain and can be done at the consensus of everyone.
Awesome, a lot to dig in there. I guess like taking it at maybe the first glean of it. So the protocol level, so there's multiple parties that are going to be interacting. There's the people who are submitting tasks that want to train some sort of model. You also have the people who are actually doing the compute and solving the task. You have verifiers on the network as well. Maybe it'd be great to hear a bit about why the protocol decides specifically and what each party does in the network.
Sure. Yeah. So ultimately, you can think of the chain itself and the machine learning work as sort of two separate areas. On the machine learning side, it's relatively simple in terms of roles. So you've got somebody who has a GPU or has a chunk of hardware that's capable of doing work. They're the person that is going to provide that hardware as a resource to somebody else. You've also got the person submitting the task who is going to use that resource. In the simplest case, you just need those two parties. In order to prove the work's been done correctly, we need to generate proofs on the original computing party. So the solver does a bit of extra work. They train a machine learning model, but at the same time, they generate these proofs that can be checked by somebody else. And then we need another party who's capable of running that machine learning training task to rerun small portions of it and check proofs. So they're the verifier. So essentially, if you have a GPU, you can be a solver or a verifier. Either you're doing the work or you're checking somebody else's work. And if you need machine learning work to be done, you're a submitter and you just submit tasks to the network. So those parties all kind of interact and they do the work that they need to do, and that kind of solves the machine learning side. Separately, the chain is the trust portion. It's the bit that breaks any kind of dispute. And that chain sits in between those parties and just handles the communication. So if I am computing a machine learning model, I'm training the model, I'm generating the proofs, I will send those proofs via the chain to somebody else in the network. So the chain can say, yes, I've received this proof and it's been checked by somebody else, and yes, that's been checked, and it becomes that kind of central ledger that has all of the kind of agreed upon interactions that have happened throughout time, essentially. The final thing that the chain performs is a tiny operation, which is the proof of the overall computation. It's not to get into too many details, but at the end of a dispute between two parties, between a solver and a verifier, you essentially are comparing Merkle trees that cover a machine learning computation. You can whittle those Merkle trees down in a bisection game via the chain, so the chain is always agreeing what's happened in that kind of communication. And then the final point that you get to in that Merkle tree will be a single operation. And it'll be a single operation that can be performed by the chain. And via that kind of path through the Merkle tree, you can prove that if the chain does this floating point operation or it does this matrix multiplication, the output that the chain gets will match either the original solver or the verifier. And then we can decide who was correct in that dispute. But ultimately, you can see them quite relatively separately. It's a distributed ledger that everyone can agree on interactions that have happened via that ledger. And then there's the solver, the verifier, and the submitter, all the kind of interested parties either providing a resource or using a resource in the system.
Really interesting. And I guess maybe talking about some of the really challenging problems that you have to solve to make decentralized compute viable. So the kind of training that you guys are looking at doing is on deep learning models, very large models. And inherently, if you think about training a large model over a decentralized network of distributed compute, there's this problem of latency, which is I'm sure like a very difficult problem to solve. There's techniques of like parallelizing models and training. So what kind of solutions are you guys, or it'd be great to get a framework kind of on that problem that exists and what kind of solutions you guys are looking at to achieve.
Yeah, sure. So we kind of see the latency bandwidth problem. And then the latency bandwidth problem is essentially, if you look at how a very large model is trained right now, it's going to be on a hyper-connected cluster with InfiniBand between the nodes. You're going to have really fast communication. You can do lots of techniques like tensor parallelism, where essentially you're just sharding the tensor and allowing it to be split across multiple nodes. But because the communication is so fast, you can essentially sort of treat them as like the same node. You don't have that kind of luxury in a system like we describe. So you've got nodes theoretically all over the world. They're going to have heterogeneous latency and bandwidth between the nodes. You're also going to have heterogeneous devices themselves, and that does introduce lots of problems. I say it's the second biggest problem because verification to us is the largest problem. You can't build a network like we described if you can't verify that a trustless party has actually done the work that they performed. So you can't even get to the scale to have the second problem unless you can solve the trust problem. So Jensen so far has been much more focused on the trust problem, but with the latency bandwidth problem, essentially we see kind of two paths. The first path is sort of like short and medium term, and the second path is much more long term. And the first path, the short medium term path, is essentially to treat this as one big optimization problem. So instead of assuming that you have super fast interconnects and training a model with all of the kind of parallelism techniques that we have, so model parallelism, data parallelism, workload partitioning, instead of just using all of those and kind of throwing them at the cluster, you would weight the connections between devices based on the communication speed and essentially more deliberately do the trade-off of communication and compute. In a distributed systems context, you're always kind of trading those two things off, and you do have quite a bit of leeway to swap back and forth. And essentially, if you look at the overall system, you can just treat this as an optimization problem. You can optimize the amount of communication that is done in the different places, and you can get much closer to state-of-the-art models that are trained in a data center. But you're never going to get kind of fully to those models. The reason you're never going to get fully to the performance of those models is that those models have been designed specifically for those infrastructures. So the machine learning world has kind of progressed down one path in the space of possible paths that we could progress. And that progression has happened because a lot of the researchers who are proposing the new model architectures have access to those clusters. So they're incentivized to build models that work particularly well for these hyper-connected clusters. It's kind of a moat for those research teams or those organizations. We're very interested in what happens when you kind of open up the space of possible places to develop these models. And the very long-term view, the kind of second approach, is to essentially build entirely new model architectures. There's growing research in that area. There's a few teams working on open collaborations. The HiveMind team from Yandex have done some really good work on what happens when you get volunteer compute and then you build language models or language model-like models over compute that's provided by anyone in the world, but it's already trusted. And Jensen takes that to another kind of level by saying, okay, now we don't need to trust anyone. We can connect on any device. The big, particularly interesting thing that unlocks then is massive, massive scale. So right now, with this sort of original path where we're building models for these hyper-connected clusters, you get to a kind of point where in order to get more scale, you need to build a bigger data center. You want to add another 1,000 GPUs to this data center, you're going to have to find a new one to put those GPUs in. That gets more and more and more expensive. So we were kind of progressing along that path, but that was getting more and more and more expensive. Jensen wants to kind of sidestep that and essentially say, okay, instead of eking out slight size increases, let's just remove the size limit and say you can use absolutely every device in the world, but there's going to be slower interconnects and you're going to have to build models in a different way. One of the particularly interesting routes is decentralized mixture of experts, where you've got loads of kind of student-teacher models involved in the system, and the communication is between these sub-models, rather than having one massive meta-model where the communication has to be really fast, because you're essentially just sharing parameters all the time between devices.
And I guess like taking one step back to the other problem that we were talking about around verification, there's that counterexample of when a task is being done, and if you're in a trustless, decentralized network, there needs to be an arbiter of truth, and that ultimately is the chain. But other than replicating the work specifically, I know you guys are looking into certain pinpoint mechanisms to kind of like verify segments. It'd be great to get a kind of overview of what that research looks like.
Yeah, sure. I think so. If you just sort of look at the problem of, okay, a completely untrusted device has done this computation, how do I check it? The sort of most naive way to check it is essentially say, we'll get somebody else to do that computation. You do the entire computation, as long as it's deterministic, we can just compare the outputs and say, was this done correctly? But in a completely untrusted setting, you don't know if you can trust the extra person who does that computation. So then you think, well, how can I trust the consensus? Maybe I need to get a majority of everyone involved to do that computation, and that rapidly gets far too expensive. There's a piece of research called TrueBit from 2017, 2018, which essentially showed how you could prove computation that was done off a chain to the consensus of a chain. And the kind of consensus of a blockchain is essentially the best we can get as to like, does everyone agree, has this computation been done correctly? And TrueBit does that by incentivizing people to redo the work entirely and then challenge and have this kind of like fraud-proof optimization process where you can challenge the person who did the original computation if you disagree, and then you can go into that arbitration game with the chain. When you have a system like that, you need up to about 6 or 7 people to recheck the computation before you can be sure at the kind of Byzantine fault-tolerant level of Ethereum that has been done correctly. But that leads to 6 to 7x replication of a task, which for a small computation, maybe that's not an issue, but if you're training a massive machine learning model, that's a 7x increase in cost. That's like untenable, essentially. So Jensen's kind of entire sort of work so far has been how do we minimize that as much as possible? And we minimize it by essentially doing a kind of deterministic audit process, but much fewer than the whole computation, much fewer segments are checked. And when you do that, you can say, okay, we do the entire computation, we'll take 100 checkpoints, we'll check 10 of them, and we've only got sort of 10% replication, but where do you target those audits? And we use a relatively complicated system of zero-knowledge proofs to generate out the loss value of the model. So we know how well the model is training, we know when big updates are happening, when small updates are happening, and then we use that information to target those audits in a really deliberate way. So we know, essentially, if a big update has happened, it's easy to hide malicious behavior or lazy behavior. So we target audits in that area, and then a verifier will just be rerunning a small checkpoint just from that area. And that verifier will check that they get the same results. If they get different results, then, as Rishan said, we step into this pinpoint protocol bisection game. And that pinpoint protocol bisection game is essentially when you do the computation, every single step in that computation. So if you treat it as a graph, you've got a set of layers that are being computed. Each of those layers is hashed. So the output layer is hashed. You get a big list of hashes. You generate a Merkle tree from that list of hashes. And then from that Merkle tree, you can compare the roots and see if that computation is identical. It's a little bit more complicated than that. You do it on a symbolic representation and then a concrete representation, but you can think about it as just a tree with a root hash. When you've got those trees, if those root hashes don't match, then you can step down the tree essentially and figure out where in that tree did we disagree. And theoretically, there should be a single leaf node essentially where the two parties disagree, and that leaf node represents a small enough computation that can be performed by the chain. So the chain does that computation, and then because it's a path through the Merkle tree, you can trace that all the way back up to the root and say either the solver was correct or the verifier was correct in this instance, and then we can solve that dispute overall. But yeah, like before we get to that dispute, we have to whittle down the computation to be small enough that it makes sense to step into a bisection game. Which is an annoying but difficult part of this. Yeah.
Definitely a lot of open-ended, interesting problems of research, and I guess in the remaining time that we have, it'd be great to throw over to some audience questions that we might have.
Yep, great. We got audience questions. Raise your hand. Keep your hand up if you want to ask a question.
Hi, thanks. About the efficiency side, do you think it's going to be more and more mining center or the mining cluster, or just will be more decentralized? Like everyone could just contribute by their own computational devices or something. So I really like if you're going to do some computational heavy model, you will definitely find a more efficiency center. So that is going to be better. So I was just curious, what kind of classes will be more decentralized to just join the Jensen network?
Yeah, so ultimately we want the Jensen network to be as decentralized as possible, so as many devices as possible can connect up and do work. The kind of gold standard that we'd like to get to is things like every iPhone could do computation on Jensen. They've got good neural processors in the iPhones, they can do decent work. In order to get there, you need the granularity of a task in Jensen to be very small, though. So it depends on how we can compose those small, kind of like very granular tasks into one larger task efficiently. But that entirely depends on the direction that model development goes. And so if model development does go in the direction that we think it will go, which is lots of smaller models all communicating with each other rather than one big kind of like meta model, then there's loads of different sort of architectures that you could propose that could take advantage of this system. I think the way that we think about it is we don't want to be the people who propose those models. What we want to do is distill machine learning tasks into something that can essentially treat compute as a commodity. So right now, compute is this like heavily capital intensive. You have to kind of get the best devices and you need to have them in the right cluster configuration and things like that. We want to kind of move that away and make it a little bit more like electricity. It's basically just available. It kind of has a unit cost. If you need more of it, you just buy more of it at that unit cost rather than having to kind of buy the specific devices. And I think we can get significantly closer to that than we currently are. I don't think we'll ever make it like a full, complete commodity where you never even think about the devices, but I think we can get significantly further towards it. So within Jensen, we mainly think about chunks of machine learning models. So every individual device is essentially doing an arbitrary kind of abstract chunk of a neural network on an abstract chunk of data. That might have been sharded in a data parallel way, it might be sharded in a model parallel way, or a partitioned way. We don't really care. It doesn't matter. We can verify that work in any case, essentially. As long as there's inputs, there's outputs, and there's some ML computations in between, which are probably matrix multiplications, then we can verify it and it can exist on Jensen. We'll do some optimization work to show what you can get out of this network. But what we're really interested in is seeing how other people can use it. And realistically, we think an ecosystem will spring up where people can kind of come along and say, our value is we are the best at optimizing the use of Jensen. So we'll get companies that say, hey, we can build language models best over the Jensen network. And other ones will say, hey, we can build image models best over Jensen. And then this rich ecosystem develops where people have value propositions of, we're just really good at optimizing over highly distributed hardware. And then Jensen kind of fades into obscurity a little bit. Everyone forgets we're there, but we're underpinning absolutely everything. And the way that machine learning training work is done has changed. And machine learning developers themselves don't even think about devices anymore. They don't think about SSHing into a machine and using a GPU. They just think about sending it out. They package up their model, they send it out, it trains somewhere. Maybe it's one GPU, maybe it's 1,000 GPUs, maybe it's 1 billion iPhones. They don't really mind as long as it gets trained. It's similar to the way serverless progressed within the Web 2 world, where application developers used to have to think a lot about how they were going to deploy their web apps. And then Heroku came along and you just packaged up your kind of web app, you were very good at developing it, and then you just sent it out to Heroku and it would deploy somewhere. We see the same thing happening with machine learning.
Wonderful. So thank you guys so much. I wish we had more time for questions. These guys will be around, and again, the side rooms are available for longer discussions. So thank you. Please give it up for our panelists.